we're going to look at a lot of ideas. So we're going to look at something called the unit circle. We're going to look at trig ratios, and we're going to look at sinusoidal waves or functions. Okay. Very first thing we want to talk about is we're going to try to establish what the unit circle is. Let's do this in black. So we'll establish what a unit circle is. So we're working with, we'll call this like waves in trigonometry. Now I'm going to draw a very poor version of it here, but luckily we have some graphing software which will make a much better one. But we do want to have an idea of how to do this by hand. So I'm putting these points so that I can try to make a circle, which I won't do that great of a job at. As terrible as it is, that might be the best version I've ever done of this. So the reason we call something a unit circle is essentially a circle that has a radius. So the radius is the value of 1. Okay?
Yeah.
So in other words, it's 1 unit. We don't know what the unit is. We can apply it to anything. It could be centimeters, meters, kilometers, millimeters, whatever you want. So the idea is this is a scalable circle that we can create. This circle is important to us because what we can do is we can create triangles from points on the circle. Okay, so I can make a little point here, and it turns out I can make this nice triangle, and this triangle helps me solve for positions and angles in this circle. Okay. It turns out that these circles, they follow a wave pattern. Okay, so it's the idea if I'm going around the circle, I'm actually making a triangle. So we're going to show you a little version of that. Is it over here? Yes, it is. So this is the idea. I can't pull from there, but I can do this. So we have our unit circle here, and if I play this, you'll notice that this is a triangle constantly being formed around the unit circle.
Yeah.
I'll probably stop there and come back. This piece is important because it turns out we've already learned a bunch of triangle information, and we're going to start to apply it to this. Are you familiar with your special triangles at all?
No.
No? So have you ever seen, usually there's 2 triangles they'll try to teach and have students memorize, just because they're very scalable and they help us get around the unit circle. They give us some insight to some particular points. So one is a scalene triangle, the other one's an isosceles triangle. They're both right angle triangles, and these are also scalable. You can make them as large or as small as you want, but a common way of remembering their dimensions is the 2 legs of the triangle are 1, and the hypotenuse of one is √2. And then the angles, they're both right angle triangles. The other angles here will be 45 degrees, or it will be pi over 4. Both the same, just depending if we're working on radians or degrees. Have you guys worked with radians yet?
No.
No? Okay. So I'll save radians for another day. But they're very, very helpful for what we're actually going to do. And I might refer back to it at one point. Okay? So this is 90 degrees. And you know what? If we're working in radians, this is technically 2 pi over 2. So we'll say these are equivalent. The other triangle is this one. It is 1 √3 and 2. So it's the idea of 1, 2, 3. So you have a 1, 1 triangle. I'll put it here. 1, 1 √2 triangle. And if we know Pythagorean theorem, we can essentially build that each time. And we have a triangle that is 1, 2, and √3. So it turns out √3 is not as long as 2 is. And then we have opposite angles of this triangle, which are, again, common angles. This one here happens to be 60 degrees. This one happens to be 30 degrees. And if we were to talk about them in radians, this one is 30 is a third of that, so it's pi over 6. And this one here is pi over 3, I believe. Is that right? We double it? Yes, that's pi over 3. So the radian might be a little unfamiliar, but we'll stick to degrees to start right now. In that unit circle, we can find these exact values, okay? Now, my A is a little different. Let's see if I can get it. I want to find exact example. So this is a 0.5. Okay, so what I've created here is a little triangle. Oops, there we go. We got a triangle here, and it's got a coordinate of 0.5 and 0.866. So I'm actually going to go back over here, and we're going to try to figure out what it is we're looking at using this unit circle. Okay? So we have this unit circle here, and I said that on the unit circle, We'll call this point A. It currently has a value of 0.5, and I think it was 0.866, probably something like that, okay? This is an x and a y coordinate, okay? Whenever we're talking about the unit circle, we're referring to this internal angle around the origin. No matter where this circle ends up going, so wherever this arm, the radius, no matter where it goes around this circle, we're always referring to this angle around the origin, okay? So try to keep that one straight, because it can be confusing. Sometimes students will draw the triangles a little bit backwards. They'll sometimes draw a triangle like this, so the arm down here and put a 90 degree, but that's actually not the way to do it. So always, whatever angle we're referring to is this internal one around the origin. What this says is the hypotenuse of this is 1. It's always 1. What's really nice about that is, when we're going to talk about it with similar triangles, is, we'll refer back to these special ones, is I can create any similar triangle or any similar circle with the same internal measurements. So a triangle, or a similar triangle to the very first one we had, so I'm going to do that first special triangle. Remember we said it was 1, 1, root 2? Well, it turns out in this case, my hypotenuse is only 1, but in my special triangle, I got a hypotenuse of root 2. So this doesn't quite line up. I can't fit it into my unit circle, but I can scale this. That's what's nice about these triangles. A similar triangle always has the same internal measurements, the angles. It's always going to be 90, 45, or I'm going to always put the other one as pi over 4. Those are technically the same. It's just to try to get you used to this idea. What I want to do is I want a similar triangle of this measurement. So this is this is root 2. But I need a radius or a hypotenuse of 1. That's what the radius of this circle is. So this has to be 1. In order to do this, I need to take this value and I need to turn it into 1. Well, what that means is I need to divide. In fact, if I divide by whatever the value is, if I divide by root 2, I end up with the value of 1. Root 2 divided by root 2 is 1. That's okay? Yeah. In order for everything else to be the same on the triangle, I have to divide the legs by the exact same amount. So those legs would be 1, they're originally 1, divided by root 2. 1 divided by root 2. That's the two legs we have here, okay? So we now have legs of the triangle, and if we want to look back at our unit circle, we can probably figure out, we can now figure out distances, or in this case, those will be coordinates on the unit circle. So because I have this internal angle here, let's say I know it's going to be 45 degrees at this point, so I'm going to recreate it. We got a triangle. This was the internal triangle, and we said that its radius was 1. Its radius of this thing was 1. And it turns out this angle here we're going to say is 45 degrees. Well, we just made a similar triangle. In fact, it's this exact same triangle we've made. So we know that this distance will be 1 over root 2, and this distance is 1 over root 2, okay? So this is a coordinate technically along the circle. I'm going to imitate an arc here. So if I needed to find this, and this is the origin, 0, 0, I can find this exact coordinate. This exact coordinate would be whatever the horizontal distance is, because this is normally your x-axis. Okay, so my x value would be 1 over root 2. And then my y value is exactly the vertical distance, whatever distance this is. Turns out that's 1 over root 2 also. Okay, so what we're doing is we're using a triangle to find out coordinates along this unit circle. Or we can vice versa. They can get a coordinate and we can use it to find distances on the triangle. So why does this connect? Because triangles actually connect with all of our trig ratios. Our trig ratios, if you remember, we have primary trig ratios, which are sine theta, cos theta, and tan theta. And if you remember the primary trig ratios, sine theta is the opposite over the hypotenuse, cos theta is the adjacent over the hypotenuse, and tan theta is the opposite over the adjacent. Okay? These connect to this unit circle because there's an angle we're constantly referring to. And I'm eventually going to go back to this. We haven't actually solved this piece yet. We went through a bit of a lesson, and we'll come back to what we've created here. If I want to find sine theta, or if I have sine theta, I can find out what this ratio of the opposite over the hypotenuse is. Yeah, that's fine. So here's our internal angle. I'm going to say, what is sine 45? Well, sine 45 is the opposite side, which is 1 over root 2, divided by my hypotenuse. My hypotenuse happens to be the value of 1. So if I work this out, it ends up being 1 over root 2. That's what this value ends up being. So the ratio of sine 45 is equal to 1 over root 2. And that's some number. We can get an exact value of it if we go over here and we say, what is 1 divided by the square root of 2? 0.707. Okay, we can put that in. But you'll notice that they're always going to start to work in exact values. We're going to say approximately 0.707, I think, something like that. Okay. But we always know that sine, because we're on our Cartesian plane, we got to always kind of keep in mind that this is an x-axis and this is a y-axis. My sine's always going to be the same, actually. My sine value is going to be, if I write it in again, I have sine some angle, theta, is equal to opposite. Well, the opposite is this vertical line. If we're always referring to this angle, the opposite's this vertical line.
Yeah.
So in that case, that's actually the y-coordinate. That's the distance from the x-axis to this coordinate. That's the y value, whatever it is, divided by this long piece, which is the radius. Okay.
Mm-hmm.
Now, we may not know what the y value is because the y value is going to change depending where we move along this circle. We come down here, the y value is shorter. We go up here, the y value is taller.
Mm-hmm.
But this radius, does this radius change on our unit circle?
No.
That always stays the same value. What is that value right now? Do you know? How long is this arm of the triangle, or this hypotenuse of the triangle, I should say?
Isn't it 1?
It's 1. So what we're doing here is we're actually going to find a very simplified version of this formula. Since our unit circle is always dealing with a radius 1, we could say is equal to y over 1, which is just equal to y. So another way of writing your sine ratio in the unit circle is sine theta is always equal to whatever the y value is. And you'll see they've actually written that down here, y over radius, but if we deal with a unit circle, it's just y. Now, if we scale our circle, this part's really important, y divided by r. If we decide to scale our circle, I'm going to try again, but I guarantee it's going to look terrible. I'll do a fast one. Ooh, that was all right. I'm going to scale it up. Wow, that went way better than I thought. Okay, let's say this is our original, okay? We have a radius of 1. I can apply the exact same information just to a longer radius. We'll say this one is a radius of, we'll just use 2, just to keep numbers simple. It's probably not to scale here. It turns out, no matter how I make this triangle, okay, my angles are going to be the same. If you take a look at this, I have 2 right angles there. This internal angle never changed, and if we know our corresponding, might be corresponding. It's a grade 9 angle formula we want. This angle and this angle, these two here, they happen to be the same. In other words, these are similar triangles. All we've done is we've scaled up the hypotenuse. The hypotenuse of this is now r equals 2. Well, you might think, okay, now I got to find out my legs. Got to figure out how far they are. I got to figure out sine ratios if they ask us trig. But this rule actually made this really simple for us. Whatever this y value is, and we'll have to figure that piece out, but whatever that y value is, we just divide it by the radius, and we have our sine theta for that angle. Okay? So we could use some basic trig to find that out. We can scale up our triangle, and if we take a look here, if we're scaling this triangle to be a little larger, so we're taking it, I'll redraw it on the side. We had our original one at 1. Remember, this was 1 over root 2, 1 over root 2. Well, we've now scaled the circle to have a radius that's larger, so we can scale this triangle. We're going to do the same thing and scale the triangle. This is 2. Well, to go from 1 to 2, I multiply by 2. Well, my legs will be the exact same. Since all the internal angles happen to be the same length, we're going to scale this leg by multiplying by 2. And if I multiply by 2, and I want to keep it an exact value, it's just 2 over root 2. 2 over root 2. And I can do a little side calculation. That's like taking this 2 times 1 over root 2. I turn it into a fraction, and I multiply the numerators by each other and the denominators by each other, and I get that value. So this, turns out, is my y value. So 2 over root 2. If I want to find my sine of 45 with a larger triangle, I say sine 45 is equal to y, and the y value is 2 over root 2 divided by whatever the radius is. And on our bigger one, our radius is now 2. And then we go and simplify. If I go to simplify this, this actually ends up as 2 over 2 times root 2. And then when I simplify one more step, this ends up as 1 over root 2. But this is the exact same answer we found before. If you notice, we had 1 over root 2 is sine 45. But we did it on a bigger triangle, on a larger circle, and we got the exact same ratio.
Yeah.
Which is absolutely correct. Sine 45 always keeps the same value here, no matter how large the triangle or the unit circle we're working with. That's why they call it a ratio. This ratio is always the same. And that's the trick to trying to understand this idea of a unit circle and a couple special triangles, is that their ratios always stay the same. So what we're going to do is we're going to zoom back in, and we're going to take a look at the other two here. So we've kind of taken a look at y. Turns out y is equal to, in our unit circle, sine theta is equal to y over r. And if we're talking about, I'll write a little title here, one unit circle, I'll call it, then sine is just equal to y, because radius, I'll say r is equal to 1 in that case, okay?
Yeah.
We go back to cos. Well, if we go take a look here, cos, remember we're always referring to this angle here. Cos is the adjacent over the hypotenuse. Well, it turns out for the adjacent side is the x-axis.
Yeah.
That's what we're dealing with, the x-axis. So we don't need to know the value. We can just find out whatever the x-coordinate is. And sometimes we're forced to figure that out. But that ratio will always be the x value over the radius. And if we're talking about the unit circle where the radius is 1, cos theta is always equal to x. Nice. That really simplifies things. We can use this as a general set of laws for our unit circle. And finally, tan. Still referring to this lovely internal angle here. Tan is opposite over adjacent. Okay, so that is opposite was our y value, and the adjacent was our x value. Now in our unit circle, r is not a part of this equation. It doesn't change anything. Y will still be over x to find out tangent. But if we are ever given coordinates, okay, if we are ever given the coordinates, so say they say x, y of something, and I need to find sine theta or cos theta or tan theta, I don't need to do anything with triangles. I literally just take these values, okay, other than finding the hypotenuse. I do have to find the hypotenuse, assuming that this isn't a unit circle. Maybe it's several units. But as soon as I figure out what r is, I can instantly have these ratios. I know that this is y over r. I know that this is x over r. And I know this is actually just y over x. I can always find those ratios. Okay, so there's a way of kind of relating our unit circle to these triangles, to our triangles and to our special triangles. But there's way more to this. I want to show you another idea. So we go over here. So we got this lovely unit circle, and we show it going around and around and around. And it's a stagnant graph. This is not a graph over time. We're actually like reversing. So depending on what our domain is. So I'll give you an example of domain, because a lot of these questions will deal with the domain of something. Oh, that one's a little let's move over this screen. If they ask me for my domain, and the domain is usually dealing with x, okay? They'll say x, maybe they'll say x is greater than or equal to, ooh, that was terribly done, to 0, and x is greater than or less than 360, okay? This is working with degrees. If I were to work in radians, that's the idea of 0 less than or equal to x is less than or equal to 2 pi in radians. And we'll talk about what a radian is in a little bit.
Okay.
I'm going around this circle. That would be positive 360 degrees, okay? But they might also give me a domain. Oh, it does not want to give me undo. There we go. But they also might give me a domain, something like this. Negative 360 degrees. Greater than less than x, greater than less than 0. That would be starting here and just going the opposite direction around this. Oh, much better when I have something to trace. We're going in a negative direction, okay?
Yeah.
This unit circle also makes a really nice connection to something called cast. Have you talked about this at all? No. Okay. CAS system tells you which of your sinusoidal functions are positive in certain quadrants. So this is quadrant 1, quadrant 2, quadrant 3, quadrant 4. It turns out all of my functions, sine, cos, tan, all positive if you're in quadrant 1. If we come over to quadrant 2, actually only sine is positive. Okay? Cos will be some negative value, tan will be some negative value. In the third quadrant, tan's the only one that's positive. Tan will be some positive, and then your cos and your sine, both negative values. And finally, in this quadrant, only cos is a positive value. Tan is negative. Whoops. Tan is negative, and sine is negative. Okay.
How do I find if those three are positive or not?
So we'll get to that when they ask us a question, because it really depends where we are at this place. What I want to do, though, is we talked about going backwards. So this would be the reverse. This would be forward. But that can be hard on a graph like a unit circle. Some people pick it up really quickly. But what's nice to show is this little idea here, is that a circle, as we go around this circle, we can actually look at it as a wave over time, as opposed to just staying in a stagnant place and rotating all the way around. You see how this yellow angle is constantly getting larger and larger and larger, and then you'll notice it stops and repeats. So it turns out these ratios, or these x and y values as you go around a circle, are, they call it sinusoidal. Periodic also, which essentially means that they repeat. It's a repeating number of answers, no matter how far we go. And when we write it out this way as a wave, we're elongating over time, or depending on degrees in our case. So if we take a look here, this is the idea of a wave. Now this one's got a bit of a different amplitude to it, okay? But this would be the wave. And these are potential answers for, this one's a little trickier. It's got cos on it. Can you give me a simple one here? Here we go. This is nice. Okay. This here happens to be a cos wave. Okay. And as we go down, we get back up to the exact same values. This is the idea of a rotation all the way around a circle.
Yeah.
And all the way around a circle, 0 to 2 pi. This is when we start to talk about radians, 2 pi. This is how long it takes to go around a circle. 2 pi is related. Oops. I know there's a lot of info here. We'll try to take a bird's eye view of it. 2 pi is related to a circle because, give me one sec. Bring this over. There we go. If there's an old rule for going around a circle, if you want to measure the distance, and this is called the circumference of a circle. Circumference of a circle happens to be diameter times pi, okay? Well, I can write diameter as a radius. In fact, we always want to write things as radius. There's a lot more rules around circles dealing with radius.
Yeah.
So a radius tends to be 2r pi. If I rearrange this as a rule of multiplication, it doesn't matter the order I multiply. I can write this like this, 2 pi r. Well, r, the question is, what the heck is r? Because I've seen 2 pi before. If I jump back to my other graph, 2 pi is how long it takes to get around a circle, or when this wave starts to repeat its period. So that happens to be what circumference is. We're actually just talking about circumference. But the tricky part becomes, what is r? Well, r is a radius of a circle, but that's a straight line distance. We're used to dealing with the circle itself. So how do I make, oops, let's jump back in, here we go. How do I relate this idea? Well, it turns out r, or radius, is the distance around an arc that is the same, call it a radian. This distance around the arc is the same distance as this leg here, which is the radius. And if this is the center of the circle, this distance to here would also be the radius. So this part here is equal to a radian, or a radius. So that's how we measure a circle. It's not nice. This would be actually 1r, and it's a really odd ratio. I think it's like 57 point something degrees. It's not a wonderful one. And if I go up here, this happens to be like 1 point, oh geez, what would it be? I don't know, like 1.567, I'm doing a serious estimate here. Radians. These are nice numbers when I get to like 90 degrees. 1.67 radians. I don't know. That's not wonderful. This one happens to be 3.14 approximately radians. That's not a great number to remember.
Yeah.
But it turns out 3.14 ... is actually pi. So we don't write them in these real numbers because it's way too hard to write it that way. So we start writing things as pi, which relates back to the circumference of the circle. And it turns out this one is pi over 2 because it's halfway. And then if I go over here, we're 3/4 of the way around. So I might say 3 pi over 2, because remember this one is pi. And if we do a full rotation all the way around, this is 2 pi. So rather than writing 6 point blah, 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 some estimate or some real number, I write these things in pi's. And then I have an idea of what a radian is. A radian is this. It's what we're saying is 2 pi radians. This is 1 radian, so we're multiplying by the radius of a circle. So these are all the connections between these things. And each of these is a tool you can use. Think of that wave that you've learned about is just really connected to our unit circle, which are all connected to our triangles. All 3 of these are tools that you can use to solve trig functions. So they'll give you a bunch of algebra, which is like your sine, your tan, your cos. They'll teach you other ones like cotangent, secant, cosecant, which are all inverses of these. There's all this algebra, but we have these lovely graphing tools that can help us make a lot of sense of this. We refer to the triangles that live inside of this circle that can look like a wave, and this wave refers back to these triangles. These are all interconnected, each of the things that we're looking at here. How many things did we look at? Holy smokes, there's a heck of a lot there.